Greetings. My name is Todd Little. I'm a professor here at Texas Tech in the Educational Psychology Leadership and Counseling program. My primary role here is as a methodologist and statistician. In fact, I teach a 1 year long sequence on structural equation modeling. We start in the fall with the foundations of SEM, some of the material that you're going to see here today. And then in the spring, I teach an advanced version of it where we delve into some of the more advanced options that are available in the context of structural equation modeling. Now, this short lecture is on the relationship between exploratory factor analysis and confirmatory factor analysis. But you'll notice here at the bottom point on this first slide is every SEM model begins with that confirmatory factor analysis model. It's often called the measurement model of an SEM. Now, before I delve into the, whoops, wrong one. Let's go over here. There we go.
Oh, you got it.
There. So, exploratory factor analysis, when you think about it, or you go to like SPSS and you ask for the factor analysis options, it'll typically give you two. One of them is a principal components analysis, and the other is a principal axis analysis. That's what exploratory factor analysis is. Principal component analysis is not a factor analysis. It's fundamentally a data reduction technique. You're trying to reduce the information that's contained in a large data set down to a handful of component scores that represent the information that was contained in that data set, but it doesn't have any real meaning. You don't interpret components like you might interpret factors. Now, an exploratory factor analysis is fundamentally a data mining technique. That's when you'll use EFA when you really don't have any sense of what structure might be contained in your data. And the EFA then, as an exploratory procedure, begins with extracting principal axis factors, and you'll do 1, 2, 3, 4, 5, 6, as many as you think are needed to try to get an understanding of how do the variables that are in your data set relate to one another and coalesce as factors. Now, with exploratory factor analysis, there's an art there, right? You're trying to say, well, what's the appropriate number of factors that I need to extract? Can I interpret those factors in any meaningful way? And so there's a lot of, again, ad hoc, post hoc thinking when you do an exploratory factor analysis. Now, the hallmark of a confirmatory factor analysis is indeed, I'm trying to confirm my expectation of a structure that I think is in those data, right? And so the example here I have is a simple one of positive and negative affect. There are two constructs that many people readily understand. You might have a protocol like this one. In the last 2 weeks, I have felt great, cheerful, happy, sad, down, unhappy. Well, a priori, we would expect two constructs within these data of 6 items. Right? Now, a construct is a latent variable, and this is all we're talking about. So it's something that we cannot observe directly, like positive affect, but we can observe your responses to items like in the past 2 weeks, I felt great. Well, that's an indication, a manifest variable, something we can observe that gives me an indication of what your underlying latent positive affect score might be. And the idea behind confirmatory factor analysis is to confirm that these items do indeed correlate with one another to a sufficient degree that I have a reasonable sense that I am measuring this thing called positive affect and this other thing called negative affect. Now, if I did an exploratory factor analysis of these 6 items, again, I would probably proceed with doing a single factor, then 2 factors, then 3 factors, then maybe 4 factors. Probably not much more than that, because the idea is some of these items should be going together, and I'm not going to go out to 6, right? If I was doing a component analysis, I might go out to 6 to get all the information that those component scores might give me. But for EFA and CFA, we want to identify structure among these items that gives us an indication that there really is something underlying and latent that is meaningful, that we can make policy and practice recommendations based on positive affect and not answering the question cheerful. So when we look at the raw correlations among these mood items, we see in these correlations clear structure, right? The 3 items that we think measure positive affect, great, cheerful, and happy, they correlate with each other around 0.6, midpoint 6, right? And then the 3 items that measure negative affect, well, they correlate with each other around also 0.6, which these positive manifolds of items gives us a sense that, okay, we probably do have 2 things going on here, a positive affect construct and a negative affect construct. And what reinforces that is also we see in this lower quadrant in green, 9 possible correlations between the 3 indicators of positive affect and those 3 indicators of negative affect. They all have a slight negative correlation with each other, which indicates to us as we look at this that positive and negative affect are likely to have a small negative correlation with each other. Now, when you do a exploratory factor analysis, you will allow all of the items to load on. In this case, I've extracted 2 constructs, which was the optimal relationship here. And what I have here now is what's called the loading matrix after rotation, where I see now that I have great, cheerful, and happy will have strong loadings, is what they're called. They're also sometimes called communalities. And so we see the reliable variance that is explained in that indicator by its factor. And so factor 1, I would be tempted to label positive affect because great, cheerful, and happy are the ones that represent that factor. Whereas factor 2, I would label negative affect because sad, down, and unhappy are the ones that are there. And you'll also see that we have loadings on negative affect from the positive items. And what you see there is they're small and they average 0. Same thing for the 3 indicators of negative affect. They also load on positive affect, but they're small and they average 0. Now, this is after I've done a rotation, right? So in factor analysis, you get the loadings, but then you want to take the information, and the computer does this for you. Basically, we'll rotate those 2 factors so that the 2 factors maximize their correlation and minimize the cross loadings onto the other factors. This is also called simple structure. I get the cross loadings to be as small as they possibly can be. I get the primary loadings to be as large as they possibly can be. And that arc tangent of the line between positive and negative affect describes the correlation between these 2 factors. Right? Now, one thing to note is these small loadings, the 0.06, negative 0.04, negative 0.02 for the positive items on negative affect, those are essentially 0. Right? In confirmatory factor analysis, we would say, well, they're close enough to 0 that I can treat them as if they were 0, and then I can now estimate the rotated factor solution. So here's the loadings again, and after with rotation, I see a negative 28 correlation. If I were to draw this out in a typical SEM diagram format, we would have all the items loading on negative affect, all the items loading on positive affect, and then we would draw a line connecting the 2 constructs with their correlation. Now note here that negative 28 is not a parameter estimate. It's a post estimation transformation of the exploratory factors. Right? What we can get with confirmatory factor analysis is we can estimate that correlation between the 2 constructs as a parameter estimate in the model. Now, you're saying, well, What does that tell you? Well, anytime we have a parameter estimate in a model in SEM or CFA, we can test hypotheses about it. In EFA, I can't test any hypotheses about that negative 28. I can't tell you it's significantly different from 0. I can't tell you it's significantly different from negative 50. It's just a number that came out after extraction and rotation. Now, if I convert this into a confirmatory factor analysis, I'm going to take all of those small trivial loadings that were close to 0 and treat them as if they were 0. So fundamentally, I'm now fixing them to be 0. What that buys me is degrees of freedom. Now I'm not making those parameter estimates. I'm saving those degrees of freedom. It's like money. I got money in the bank, and now I can spend that money on estimating the correlation between positive and negative affect. So I potentially have 9 possible correlations between great, cheerful, happy, sad, down, and unhappy that are all going to be channeled through the latent construct of positive affect and the latent construct of negative affect. So really, I'm going to make one parameter estimate based on those 9 possible correlations. So I use up 1 degree of freedom, and this particular model would end up having 8 degrees of freedom. Now, here's a more typical drawing of a CFA model where we have indicators generally are listed below their latent construct. We oftentimes will label these parameters using Greek representation. And here we have loadings represented as lambdas. The residual information is theta. So the residuals is the amount of variance in an indicator that is not explained by the latent construct. We have 2 estimates of the variances of positive and negative affect, and then we have the estimated correlation between the 2 constructs. Now, with exploratory factor analysis, one of the things that's not often indicated is that one of those factor loadings is fixed at 1 to identify the factor solution. In confirmatory factor analysis, we have more options to provide the identification constraint, or in this case, actually, the scaling constraint that defines what the parameter estimates will be and be interpreted. Now, there are 3 methods for scaling. One is where, in this case, I've fixed the factor variance at 1. Another one is called the marker variable method, where you fix one of the loadings at 1, like it happens in EFA. And then a third technique is called effects coding, where you make the loadings average 1, which has an added benefit of making the variance and mean of the latent construct interpretable in the same scale as the indicators were measured in. So I'm not going to go into a lot of detail there. That would be when you take my SEM course in the fall. We'll get into all the details of scales, setting the scale, and then how we might interpret it. Right now, I'm going to fix the latent factor variance at 1. So basically, I'm standardizing the latent construct to have a variance of 1. And if I was estimating the mean structures, it would have a mean of 0. So what I'm estimating, the relationship between positive and negative affect, is now going to be in correlation metric, because the variances are fixed at 1. They're standardized. That gives me a correlation between the 2 constructs. Now, we have what's called the model implied correlation or covariance matrix that is derived from the particular model that we were just looking at. Right? So all these parameters, I've labeled them lambda 1, 1, 2, 1, 3, 1, 4, 2, 5, 2, 6, 2. They all have particular meaning. Now, I can reproduce the matrix sigma, which is the model implied matrix, by basically putting my finger on one of these boxes, going up a line. So if I put my finger on great and went up lambda 1, 1 to the positive affect, and then went over the arc psi 2, 1, and then down lambda 4, 2, that reproduces the observed correlation between great and sad as a model implied correlation, which is simply the multiplication of lambda 1, 1, psi 2, 1, lambda 4, 2. Now here, I have the matrix algebra formulation of that. So we have the matrix sigma, which is equal to the matrix lambda, which is going to be the 6 loadings, the 3 on positive affect and the 3 on negative affect. psi, which is going to be the two variances and the covariance between positive and negative affect. And then we have the transpose of lambda, so we can get the cross multiplication going on between the indicators on the positive affect side and the indicators on the negative affect side. And then we add into that, onto the diagonal list matrix, the unexplained variance in each of those indicators, also called the residuals. And so you'll see in the top part of the triangle, we have what's called a just identified solution. We have 6 parameter estimates coming out of that location where we happen to have 6 observed bits of information. 3 variances, 3 covariances. Same thing for negative affect. We have 6 parameters being estimated, and then we have the 6 bits of information, the 3 variances and 3 covariances. Now in that box in the lower quadrant, we have 9 possible observed correlations, but out of that set of 9, I'm making 1 parameter estimate, which is the implied correlation between positive and negative affect. So I'm using up 1 degrees of freedom. And now what we have are 8 degrees of freedom for this overall model to evaluate model fit and the tenability that there are, in fact, 2 latent constructs here that represent what's going on with these 6 measured variables. We can estimate the parameters of this model using a number of different ways. The traditional, most likely, no pun intended there, maximum likelihood. That's the one you most often use to estimate the parameters. And it's an iterative process where it starts off with a set of guesses that are usually weighted based on generalized least squares as a start, and then it tweaks those values until it comes up to a set of parameter estimates that are most likely to have given rise to the observed data. Okay, again, I'm using literal notation instead of the Greek letters, but here are the parameter estimates when I estimate the relationships. So now with the parameters being estimated where the variances are fixed at 1 and because it's standardized, I now have loadings that I can interpret as if I square the loading, it's the amount of variance explained by that latent construct, plus the residual, in this case, 0.75 squared plus 0.44 would equal 1.0. That's the total variance in grade. Of it, 0.75 squared is explained by positive affect. Cheerful and happy, we're at 0.80. Over on the negative affect side, we're again in the 70s and 80s. Right? Now at the bottom, you'll see that I've reproduced some model fit information. I don't go into a lot of detail here now, but that's the kind of the opus of confirmatory factor analysis, is using these model fit indices to say whether or not my prior expectation of 2 underlying latent constructs is reasonably supported with the data that I've collected. So I have my chi-square on 8 degrees of freedom. See, my sample size is, in this case, is 759. Chi-square is 50.56. Well, that would be significantly different from 0. And we don't really rely on that to evaluate model fit because of its sensitivity to sample size. But we have another set of fit indices that are commonly used. The RMSEA, also called the root mean squared error of approximation, that will give us a value, a point estimate plus a 90% confidence interval. Typically, if the confidence interval is below 0.08, we consider that acceptable model fit. And then we have the CFI, the comparative fit index, which is one way to think about that is what percentage of the information did I capture in this model that was in the observed data to begin with. And so when we get to about 0.90 or higher on that fit indice, we say we have acceptable model fit. And then the other one, which is highly related to the comparative fit index, is called the Tucker-Lewis index, and sometimes called the non-normed fit index, because in the 50s it was invented by Tucker and Lewis, and it was reinvented in the 80s by Bentler and Binet. And they called it the NFI in the 1980s article. Most of us who have our traditions going back to factor analysis, we like to refer to it as the TLI. Right? In this case, all the model fit indices indicate we have a well-fitting model. Now, one thing to note is the mathematics behind exploratory factor analysis and confirmatory factor analysis are actually the same. It was in the 1970s that Yorskog, Bentler, Weeks figured out that they could actually take the exploratory factor analysis engine, go into the matrix of loadings, and actually impose the restrictions of fixed zeros on that part of the matrix. That allowed them to take the EFA engine, same mathematics, but then estimate that parameter at the top, which is the relationship between the two latent constructs. Well, that opened up a whole world for structural equation modeling, because I can also estimate that particular parameter as a regression estimate. So now, if I had an idea that positive affect predicted negative affect, I could fit this model with a regression line where positive predicts negative. Right? And that's a parameter estimate that I can evaluate now. Is it significantly different from zero? Is it significantly different from a regression estimate? Say this was a model of males versus a model of females, or a model of seventh graders versus a model of eighth graders. I can test whether there are differences between my samples with what we call multiple group confirmatory factor analysis. So it opened up a wealth of opportunity for complex modeling of data. And now what I'm dealing with are latent variables. What are the advantages of latent variables? Well, the loadings represent all the reliable information among the indicators. The residuals represent the measurement error. So what I'm doing here is I'm extracting measurement error, leaving that behind so that the relationships among the latent constructs are no longer occluded or attenuated by the measurement error. Anytime you do manifest variable regression, anything you're doing in a manifest variable ANOVA, all your parameter estimates are going to be underestimated because there's measurement error in the denominator of all your equations that you're not getting rid of. When we go to the world of SEM, all that measurement error is separated out as residual information from reliable information, those loadings, and now I get a factor score for positive affect that is totally reliable, and a factor score for negative affect that is totally reliable. And now I can ask a whole wealth of interesting statistical questions about the relationships among my latent constructs. Typically, we're going to have more than two, so we can get more levels of complexity. There's really no limit to the number of constructs that I can have in a model outside of the memory limitations of my laptop. But other than that, the sky is the limit. So lastly, here we get the implied versus observed correlation matrix. So we have sigma up top, which is the model implied matrix that I derive by using all of the, going up, hitting my finger on a box, going up a loading, over and down again. This gives me the model implied relationships. Then we have this matrix S, the observed covariance matrix. Then we have what's called the fitted residuals, which is going to be the difference between those observed correlations and the model implied correlations. And we use those residuals to say, okay, if we glance at the bottom part of this, we see that those residuals are very close to zero. They average zero, and most of them are small and trivial. There's one in there, the 0.17 between sad and great, that is a little on the high side, but it's close enough to zero. And because there's no theory that would indicate why great would have a correlated relationship with sad, we would disregard that fitted residual as being meaningless and therefore ignorable. And then all of that goes into those other fit indices that I talked about, the RMSEA, the CFI, and the NNFI, to evaluate, okay, this was a really well-fitting model that explains the observed data quite well, and we would then proceed with asking interesting research questions about the relationship between positive and negative affect. Maybe we have other constructs that might predict them. We might have groups that we're interested in comparing. All of these come into play now that we have a well-fitting model. So, any questions on any of this?
Yeah, so Dr. Little, first off, thank you so much for being willing to talk a little bit about it. I have a couple of questions that I think will probably come up. I really appreciate what you said about how there's no limit except for the computing power to the number of factors. That being said, what do you think a good number of the latent constructs is in a structural equation model? What do you kind of see as like this is probably where the minimum is, and what you see kind of on average?
Yeah, and that's really going to depend a lot on the theories that you're working with and what kinds of things you're interested in. Like if you're looking at something like motivation in the school uh, context, you might want to have maybe DC and Ryan's a continuum of motivation that has four constructs: intrinsic, extrinsic, introverted, or interjected, and identified. But you might want to also have particular self-beliefs. Now, in this case, I might go into the world of action control theory and look at agency. So you might have agency for ability, agency for effort, agency for access to powerful others, i.e. teachers, and maybe agency for luck. So now we're up to 8 constructs. And then I would probably want to have important outcome variables. Well, am I looking at well-being in school, overall well-being? So I might have positive and negative affect as my outcome constructs, looking at how motivation and agency predict them. Or I might have school-based outcomes, the grades in various classes, maybe the Texas board scores. Those would be my outcome constructs. So now we're looking at around 10-ish, right? So I think for many well thought out research areas, there's probably going to be about 10 to 12 constructs that you're going to want to identify and measure. Now, typically, if you're going to take the time to do a large scale measurement, you're probably also going to kind of embed in there other constructs that you might look at as a secondary data analysis. Right? My primary research question might be motivation and agency, but maybe I'm looking at things about parenting. Right? Bring those constructs in to your measurement system. And then at the very end, you might have a really big model where you bring the two research questions together to say, well, here's how parenting impacts motivation, impacts agency, impacts school achievement.
Yeah. I think that leads to a second question, and one that, as someone who I wish I would have had your class when I was first getting into structural equation modeling, can you talk a little bit about groups? Because I think a lot of times we have questions of men and women, or first generation students versus multi-generation education students. How do we handle those observed variables in a structural equation model? Do we do two SEMs, or is the
Right.
assumption that it's captured in the one model?
Yeah. So when you have groups like gender, first generation, second generation, uh, grade 7 versus grade 8, grade 5 versus grade 10, whatever, the you'll collect information on the females. You'll collect information on the males. Now, depending on the software package that you use, like with M plus, you used to say groups are gender. Or typically what I do is I tell you, whenever you're measuring something like gender, label that variable with whatever the high score means. So if I was measuring males as 1 and females as 0, I would call that variable male. That way there's no ambiguity as to what a high score means. If you call it gender, first thing I have to ask when I get the data set is, well, what's a high score mean? Who's coded 1? Right? So if it's called male, it's obvious. But either way, if I say groupings are male, what M plus will do is it will take that positive and negative affect model, fit it for the females and for the males. And then when you get your fit information, it's kind of a weighted average of the model fit of the females, had you fit it just to the females, and to the males, had you fit it just to the males. But in the multiple group case, we're fitting it to both males and females, and we're getting that model fit information as kind of a weighted average to say, well, yeah, this model fits well for both males and females. And you'll get like, well, um, 49% comes from the males, 51% comes from the females. It could be 60-40. That usually doesn't matter. Sample size considerations. Um, Fundamentally, I recommend a minimum of 120 for a single group SEM model. If you're going into subgroups, I recommend a minimum of 40 in each subgroup, where the sum of all of the groups gets to be about 120. So if I was just doing males and females, I would want to have about 60 and 60, but it could be 70, 40, somewhere in there, as long as the total comes out to be 120. Because one of the hallmarks of multiple group analysis is that we get to test a really important assumption that is made whenever you do like a males versus females ANOVA. You are assuming that the constructs are what we call factorially invariant or measurement equivalent, right? What we can do in SEM is we can actually test factorial invariance assumptions. And if it passes, then I know that I'm measuring the same construct in males and in females. In fact, that factorial invariance capability of multiple group comparisons really lifted the burden off of cross-cultural research, because I could go do a study in Germany and another one in the US, and through the virtue of factorial invariance, show that I'm measuring the exact same constructs in the German sample and the American sample. And now when I see differences in the latent constructs, I can attribute those to being true cultural differences and not due to a failure of my instrument to not measure the constructs the way they should have in the two different cultural contexts. So factorial invariance is really one of the key features that's a hallmark of the multiple group SEM world.
Awesome. That was it. I don't know if you have any final words, but we definitely appreciate you, Dr.
Yeah,
Little.
no, definitely. Please, you'll qualify to take my SEM 6301 starting this fall after having taken this class. We'll go into this in a much slower pace in a way that we scaffold the learning that by the end of the semester, you will be able to do a multiple group CFA. And then when we get into the advanced part of it, we'll add in there some to the ability to answer your interesting research questions so that at the end of the day, you should be able to get your dissertation done or get a publication that would be ready for peer review. That's the goal of that sequence.
Awesome.